Hi, how's it going? My name is Carl Diaz with the Learning Resources Center here at the University of Colorado, Denver, and I just wanted to make a video on elastic objects. I didn't have one specifically. I explain a lot of them in a lot of different videos and conservation of energy, these types of things, but I wanted one specific just because it's an important concept of physics that you kind of need to know as a separate thing. It's its own little thing. So, elastic objects, what's going on? When you stretch something, right, what is it always wanting? What makes it elastic? What makes it want to go back, right, to what or makes it stretchy? Is the fact that it wants to go back to its original shape, okay? Anything elastic, when you stretch it, the thing that makes it elastic, right, means it wants to go back to original shape. So like a ball, when you bounce it, it's elastic because it wants to return to its original shape. So, right, it applies a force back to the ground that makes it push back up, right? But anything elastic, we in physics like to use springs as a good example of elastic objects because it lets us really explain what elasticity is. Because even with the spring, right, a spring when it's not stretched has an original, right, it just sits at equilibrium, not stretched, displaced in any sense. That is its original shape, is what we can say. And when we take a spring and we stretch it, we're stretching the spring from its original shape, and when we let it go, what does the spring do? Return back to its original shape, right? So springs are elastic, right? That's the best way to think of something elastic. But all things, atoms, right, work like springs. They're also elastic, right? And so when we look at objects, other objects besides springs, we see that they're elastic in the same way that a spring is elastic, which means these objects want to return to their original position. Now, things that aren't elastic anymore are what we call plastic. That's the word plastic. That's where it comes from. When things are no longer elastic, which means they don't have this restoring force that's bringing them back to their original shape, that's what we consider plastic. So just keep that in mind as well. But, right, again, what makes something want to return to its original shape or really giving things those elastic properties is what we call the restoring force. Okay? And the restoring force is part of Hooke's law, and the restoring force is really described. Now again, I'm not deriving things for you, that's the point of class. You need to go to class, right? But if you're just using these to just kind of, do different things with they're good, right? But I'm just not deriving it for you here. That's not the point of this video. All right, just so that you keep in mind, it's just to describe these things to you. So the restoring force, right, is really described by this K and X, all right? And there's also a negative sign there, but it's not always negative. All it's really trying to say is that restoring force is going to be opposite of the displacement from equilibrium. Okay, it'll always be pointing. You can see that restoring force is always pointing towards equilibrium. In this case, if this was negative x, the restoring force would be negative. But in this case, the restoring force is positive, so it can be positive. So just, that negative sign just means opposite direction. Okay, of displacement. All right, so. The restoring force, what we talk about is that K, now yeah, K can be described as a spring constant, right? But K is, again, this restoring force is describing anything that's elastic. And so that K is really the stiffness of an object, stiffness of the spring, stiffness of this marker, any object. K is trying to describe the stiffness of that object. X is always trying to describe the displacement from equilibrium, right? So if I have, something that is stretchy, right? It's going to have an original length, and then I stretch it, right? Well, that's going to be displacement from equilibrium. Or if I have a spring that sits at original length, right, unstretched, right, and I stretch it, well, that stretch, how much I stretched it is how much I've displaced it from its equilibrium. How do we know what its equilibrium is? Because it's where it naturally sits at rest, all right? So that's what that X is. It's displacement from its equilibrium position. But if equilibrium position is a weird way to say it, just say it's displacement from its original shape, right? All objects have an original shape. When you change the shape, that's what X is equal to, how much you're changing the shape, right? By how much. That K is how stiff that object's gonna be, how hard it is to bend, or how much it's gonna want to pull back to its original shape, all right? So that's what the restoring force is, and that is Hooke's law, okay? And that's what that's trying to describe. And again, restoring force is just trying to describe why things are elastic. Well, it's this force that's pulling them back to their original shape. And like I said, as we can see with the box on the spring, right, whether we displace it at max displacement this way or it's max compression this way, there's that restoring force. It's always pulling it back towards equilibrium, okay? And acceleration will always be max there. Again, I do another video on boxes and springs where we talk about the kinetic energy and potential energy and those points, and we kind of talk about it down here. And also the force and acceleration and things like that. Acceleration being max at these points. But just keep that in mind, okay? The restoring force. What makes this spring go back to this equilibrium position, right? That red marking the equilibrium position where this box where the spring wants to sit naturally, right? That restoring force. It's always bringing that spring back. That's what makes a spring elastic or makes it stretchy. That's what makes all objects elastic or stretchy, okay? We also know that objects, elastic objects, they have energy associated with them, okay? Like once you stretch it, right? Once you stretch a spring, right, there's energy in that spring because when you let it go, it gets kinetic energy. That potential energy that's in it turns into the kinetic energy, right? In the spring, right, it'll bounce back and forth. Like if I have this system and I have a box and I stretch it, this thing's going to oscillate back and forth, right? And that's because the object gets potential energy, and the potential energy converts into kinetic energy, and then the kinetic energy converts back into potential energy, right? And we know when a box is oscillating that when it's at equilibrium, the only energy that's there is kinetic energy, right? So the total energy of the system when the box spring is at equilibrium is going to be equal to just the kinetic energy of the system. We also know that when a box or a spring is at max displacement, the total energy will be equal to the elastic potential energy. So we have a lot of different types of potential energy. Elastic potential energy, or the amount of energy that's stored in an elastic object, is going to be equal to 1/2. And again, K is the same thing here. It's the stiffness of the object, and X is going to be displacement from equilibrium. Now again, this isn't just for springs. I'm describing them in terms of springs, but these things are true for any object that's elastic, okay? The elastic has the object is going to have a restoring force. It's going to be bringing it back to its original shape. And when it's stretched, when it's not at its original position, it's going to have elastic potential energy associated with that. The object's going to have a potential energy associated with it, okay? No matter if it's a spring or this, right? Like if I stretch this and let it go, there was potential energy in the bend, right? So that's the thing. It's not just springs. There's potential energy held in things when we stretch them, when we move them from their original shape, but they're elastic and they have that restoring force that wants to bring them back to equilibrium position. They will have elastic potential energy in that point. Again, when things aren't elastic is when that restoring force isn't there. The object doesn't want to return to its original shape. That's when something isn't elastic. So any object that returns to its original shape is elastic. Even your bones. You can't see it, like this marker, you can't see much of a change, but it's elastic, it's bending. Your bones compress, right? They're elastic, right? So hard materials can be elastic because when you get off your legs at night, your bones return to the original shape, all right? So they're elastic, all right? Don't think just, soft things are elastic. Hard things can be elastic. The thing that's defining something that's elastic is its ability to return to its original shape, okay? And so when it is stretched, whether it's, no matter which way it's stretched from equilibrium position, in the case of the spring, we have at both those max displacements, right, or any displacement, right, the total energy will be equal to just the potential energy of that system. So however stiff the object is and however far you displace it from its original shape or its equilibrium position, that's how much energy the object will have at those max displacements. But if something's oscillating, right, like this thing would be oscillating, it goes from here to here, right, then we'd go back to equilibrium position and back here, right, and just going back and forth, it's going to switch, right, it's going to go, now again, it's not sitting still, but just imagine that, right, this thing's oscillating, so when it gets to equilibrium position, it's going to have max kinetic energy. When it gets all the way out to max displacement, all the kinetic energy will convert into the max potential, or into the elastic potential energy. So the total energy of the system will just be equal to that. And the same thing here, once it comes back to equilibrium, it'll be then again equal to just the kinetic energy. And then when it gets to the max displacement again in terms of compression, all that kinetic energy will then be put into the elastic potential energy. So it'll go back and forth, right? And we can see that really well when we look at these boxes when they're in between where those red dots are going to be the equilibrium position, the natural position of the spring. And this blue, right, is the max extension, and this purple is the max compression, just like I had marked over here. But we can see when we look at this box, somewhere in between equilibrium, where we would have just kinetic energy, or max extension, where we would just have elastic potential energy, we see that the total energy of the system will be equal to a little bit of both, right? Because in between there, in between the equilibrium position and that max extension, the kinetic energy is converting over to the potential, the elastic potential energy. And once the box is here and starts to move back to the equilibrium position, right, it's going to come all the way out here. Once it starts to move back to the equilibrium position, all the potential energy is going to convert into the kinetic energy. So once it reaches here, it'll have max kinetic energy, but it doesn't stay there. It immediately starts to move this way, and so the kinetic energy that's there starts to convert back into the potential energy, which is right where we have a max displacement here. And so that's what's going on. So anywhere in between max extension and equilibrium, you're going to have a little bit of both. Okay, a little bit of both energies, where this X here is going to be your position from equilibrium. Just don't forget that. Okay, that's what that X is that you're looking for. Okay, or if you're using this max extent, if you know the max amplitude, you can kind of use, well, no, not in this case. Sorry, I take that back. So just in these cases, I was thinking of a different situation. So just in these cases, keep in mind that X in there, no matter which equation, is going to be the displacement. This is how far you are from equilibrium. Okay, or your original shape. Okay, so the total energy, anytime you're in between max displacement and equilibrium, will be equal to a little bit of the kinetic energy. Now that's not max velocity. Max velocity occurs at equilibrium, but you will have some speed, right? And you'll also have some potential energy at that point. So that's all this is saying, right? What they'll be will depend on the question, right? This is a concept video, so this is just trying to show you the concepts. If you have to solve for the speed of the object at that point, you want to use one of these reference points. You want to say, okay, either the thing started with max kinetic energy, and then that's going to be its final energy when it gets to that point, or it started with max potential energy, and that's going to be the final energy when it gets to that point. Either way, and I'll do a video for you for that. That's how you use that. But just at that position, what I'm saying is its total energy will be equal to a little bit of kinetic and a little bit of potential, elastic potential energy. Same thing with this position. In between displacement and equilibrium, the energy of the system right there at that point, when it's in between that max and equilibrium, no matter if it's fully on the compression or on the extension, will be equal to some kinetic energy and some potential energy. How much it will be based off the problem that you're trying to solve, okay? So keep that in mind. All right, so with elastic objects, right, or any type of object, once you extend that object past its point of wanting to return to its original shape, we get something called deformation, okay? And that's what this part over here is trying to describe, okay? So when you have elastic things, they all work this way, okay? There's going to be a restoring force. They're going to just want to return to its original shape. But if I were to stretch something and then I stretch it so far that it can't return to its original shape, I've deformed it, right? Or if you break something, right, you've deformed it, right? So when you push something past its elastic point, because this is how elastic, this restoring force is how elastic, or this potential energy is how elastic the object is. When you push something past that point, you get what we call deformation, okay? And deformation is really described by this stress equals strain, right? So we have 3 different types of strain. That's what these are describing over here. And 2 different types of stress. It's written the same way. It's the same thing. It's just you might just hear it described 2 different ways, so I wanted to write it differently. Where stress is really force over area. Okay, so how much force you're applying per area. That's what stress is. Okay, but stress is also pressure. We know pressure is force over area. So you can call it force over area stress, how much you're stressing the object, right? Or you can call it pressure. Okay. Either way, it's the same thing. You'll see I have it written as stress here, or pressure down there. But either way, pressure is still the stress, so we're still following the stress equals strain, right? So, three different ways really that we focus on in physics how to deform something. The first one is what we call tensile strength, right, or compressive forces. When you have something long and you shrink it, right, it's long and you press it in and it gets smaller, right? Or tensile strength is when you pull on something and stretch, like when you load up, like bags, backpacks, or luggage. They have tensile strength. You're going to load it up with a bunch of luggage, right? And then you're going to lift up on it, and you're going to stretch the suitcase will stretch, right? And it's going to have a certain tensile strength associated with that. And if that, if you overcome that tensile strength, the bag's going to rip and it's going to hold this permanent. It's not going to have its original shape anymore. It's going to have a new permanent shape or a new change in length, right? Its length will change, it will stretch a certain way. And again, I also keep in mind this could just be describing how far something's changing length based off of how much force we're putting on it. Even if the object isn't elastic, like let's say we have a plastic material, we can still apply stress to it. It's going to have an original length and we can deform it. Okay, so keep in mind, this isn't just for elastic things. This is how we deform all objects. But we associate it with elastic things because Hooke's law, this restoring force, this stiffness and displacement from equilibrium, we can see right here in this original, or in this first example, really, and I have this arrow pointing to this, but it's really this right here that's Hooke's law. This is also another way to write Hooke's law, okay, where, again, it's this force, right? This is just force per area, but it's this force, and it's equal to, now the y here is now describing the stiffness. That y, get what we call Young's modulus, describing the stiffness of the object. And now, instead of x in terms of displacement, we're talking about displacement in terms of length here. We're looking at the ratio of displacement for that permanent change in length to that original length. And that happens, right? Like when things heat up, right? They get longer. That's one way to describe that. There's a lot of different ways to use that, but no, that's a specific type, so that's what we call tensile strength or a compressive force. The strain is y, or what we call Young's modulus, times the change in length over the original length. Now just keep in mind, because I see a lot of students mess up with this equation, that's the change in length. So if you have an object that's 10 meters and it goes to 4 meters, okay, the change in length is 6 in there. It's not the 4 meters, it's not its new length. Now this L down here is its original length, so that would be the 10 meters. But this is the change in length, okay? So again, if it goes from like 10 to 4, the change in length is 6. So just be careful what you put up there in terms of change in length, all right? But this y modulus should be given to you, or you'll be asked to solve for it if you know how much the change in length and the original length is and the amount of force you're applying to that specific area, right? You can solve for Young's modulus, or most materials we know what Young's modulus is, so you can go look it up. Young's modulus, this S, shear modulus, and this B, bulk modulus, most objects we know what they are. You can go look them up, but sometimes the question will ask you to solve for them, but they'll have to give you this other stuff, all right? So, for tensile strength, this is how we write the stress, this is how we write the strain, where that y is Young's modulus, describing the stiffness of the object. This is the change in length and the original length, and this is just force over the area that we're applying force to, okay? The next one, in terms of deformation, so again, this is talking about deformation in terms of length. If that wasn't clear, I probably should have written that up there, but I'm telling you now that this is length deformation. Okay, and we're stretching, all right? I want to make sure you understand, because I've been saying that over and over, but that's what this is doing. This one right here is kind of where the shear modulus, but it's about equal and opposite forces. So it's trying to describe when things rub together. Like, you know, if you have a box, an empty box, and you rub across the top of it, right? Well, you're applying a force this way, but the bottom of the box, right? The box is going to have some length to it, which is what this L is, right? The box is going to have some length to the floor. And that's where the other force where friction, right? The box will be sitting on the ground, so there'll be friction moving. I'm going to be trying to push it this way, so friction will be moving this way, but I'm going to be pushing this way. The thing is that the box is like this, right? The bottom of the box, right, is getting the friction force, where the top of the box is getting the force that I'm pushing on, right? When I'm sliding my hand across, like, oh, well, I have the box right here. Like, I'm sliding my hand across the top of the box right here. Now, this box can't deform, but if it could, if I slid my hand like this, the top of the box would want to slide this way, and the bottom of the box would stay still, and the box would deform. The box would get what we call this shear stress, where it'll deform and kind of like will get side. You've seen it before. I know what you're talking. I know you know what I'm talking about. I just wish I could show you, but kind of like this right here. So see how that gets. See that angle that we get. So this is the original. This is the L right here. But if I apply a force here and here, now this force on the top of the book I'm applying this way. This force with my hand on the bottom of the book I'm applying this way. So this hand I'm applying this way. This hand I'm applying this way. And we see the book gets shear force. See the shear force there? You see it? And we see that this length, right? And then it gets the shear force. Well, now we see that there's some displacement here, which is what this X is, right? So we had its original, right, length here, and then when I apply that shear force, there's going to be some displacement from where it was originally sitting, and that's what that X is. Okay, so that's what shear force is. It can be described for a lot of different things. It's actually quite important. When molecules slide and rub against each other, that's also shear force. They can apply shear force to themselves and cause themselves to break apart, or large molecules or cells can when they slide across each other, might apply shear force to themselves and can rip themselves apart. Those types of things. They can deform themselves, right? So that's what this is. That's what this shear strain's trying to describe. And again, equal and opposite parallel forces, you could see, right? These are parallel to the surface, not perpendicular, right? I'm not squeezing the book or pushing in on the book. That's what this and this one is really doing, right? For the strain, right? I'm pulling on the object, trying to stretch it, right? But this one, right, is going to be parallel to the surface area, right? Where again, and I'll show you one more time where, right? And I can do it this way too. I can apply this force this way and this one the opposite, and I get shear force that way, or I can do it the opposite way and get shear force like that. But it's about that perpendicular, perpendicular force, okay? And so the stress is still going to be the same. It's going to be that force that I'm applying to the area, but again, that force is parallel force as opposed to perpendicular force with these. So the parallel force to the area, as you can see, this is the area. I'm pushing this way, so it's parallel to it. Right, we're going to have that force over here times S, which is what we call the shear modulus, which is just, again, describing the stiffness of the book in that case, or the object that's experiencing the shear force. That X, like I showed you, is the displacement from its original shape. So we go from here to here, right? That's a little bit harder to see there. Let me do it like this. But that's its original shape, but you're going to see it's going to slide in about that much. See it? So it was there, now it's there, right? This change, not this, but this change right here is the X. This L is this length, okay? So this would be L, the displacement that you see right here. See, so there's the original, and then you see how it goes a little bit, right? Probably not the best example. That's what X is, okay? So that's how you describe shear force, all right? And again, for this last one, this is really how things crush. So this is like a crushing force where it's perpendicular forces inward on an object, right? So again, the strain is going to be what we call V, the bulk modulus, right? Over and times the change. And now again, change in volume. Keep in mind, this is the change, not how much the length, but the change. Okay, so right, if the volume is like 3 meters cubed or something like this, and then it goes to 1 meter cubed, the change is 2. Okay, it's not 1. All right. Now the original volume would be 3 there, but the change, if it goes from 3 meters cubed to 1 meters cubed, the change is 2. Okay, so just again, be careful when we're talking about the change in here. Right. But again, the strain for crushing, right? So I should write that. This is crushing, right? Which you can do, and this is like sliding. I don't know how to really describe that one. But you know, like when you can like put something deep in the ocean, it'll crush because of this. Okay, it'll experience a certain amount of pressure, and its volume will shrink. It'll crush, right? But we can also get expansion too. Okay, so this could also talk about things getting larger, like a balloon blowing up, getting larger. Okay, so again, for tensile strength, this is how we describe it. The stress is force over the again perpendicular force to over the area, right? The applied area, so the force is being applied perpendicular to the surface area. So this is the force over area. Y is the Young modulus. This is the change in length over the original length. For shear forces, we know the stress is still, again, the force over the applied area, the surface area, right? But this force is now the parallel force, right? But this area is still surface area. S is the shear modulus. This X is the displacement of the surface, which I've shown you. And this L, again, is the separation of the surface. Like I said, if it's these two, the bottom and top of the surface, it's having the forces applied to. It's the distance between them, right? Because it's not always a book or a box. It can be two molecules, right, or cells. So just keep that in mind. That's what the length is. The length is. So this could be like the top of the cell and the bottom of the cell. Okay, keep that in mind. So the length would be how wide the cell is in that case. Okay, so just keep that in mind. What that is, and then for crushing or change in volume, right? Again, this is all deformation. We know it's the pressure, which is still just the force with the perpendicular force applied to the surface area inward, right? Which is just the pressure times the bulk modulus, which is again just describing stiffness, over again the change in volume over the original volume, all right? So I hope this was helpful. If not, go back and rewatch it. You should understand these things, understand why things are elastic. Like I said, I will make more videos describing this idea with the potential energy, but this is where I'll leave it here for now. So I'm super proud of you. See you on the next video.